Hi, physics. Mr. Janowski here. This is chapter 13, homework number 2, problem number 1. And we're not going to do the whole thing. We're just going to do, we're going to make the little sketch that we need to make. And then we're going to do part A and then part E. Because B, C, and D are just the same idea as part A. And I don't want this video to take forever. So that's what we're going to do. So first of all, let's see. Before we even get to part A, it says, imagine if the orbits of Mercury, Venus, the Earth, Mars, and Jupiter all aligned so that these planets were all on the same side of the sun, lying in a straight line. So sketch this situation below. So let's do that. Let me pick a nice color. I've got a good color. Okay, so let's start with the sun. I don't want it to be that big. I don't know why it always does this. Yeah. So here's the sun. I went with a blue sun. All right, it'll do. So the first planet away from the sun is Mercury. So I'll just call that M. Next comes Venus. So we're clearly not drawing these things to scale, but that's fine. Then we get to the Earth. Then we get to Mars, which is going to be another M. We'll just keep them straight from context. And then the next planet is Jupiter. And then Saturn and so forth, but we don't need to do all those guys. So here's our sketch. And yeah, key ideas. These are all on the same side of the sun. So maybe this is, the top-down view. And we're looking at these guys, and they're all just happen to line up. So this would be a hell of a astronomical and astrological alignment. And they're all lying in a straight line. So we've sketched that. So now, let's see. Part A. What would be the gravitational attraction between the Earth and Mercury? So I'll do it up here. So for part A, what's the gravitational attraction? Well, that's the force due to gravity. So F sub big G between Mercury and Earth. So this will be question mark. And what units will it be? It'll be newtons. And then again, B through D would all be the same thing with the different planets. And then eventually we'd get to step E. So what would be the net gravitational force of this alignment? What would the net gravitational force of this alignment be? And is it towards or away from the sun? Okay, so the net gravitational force, well, that's really the sum of the forces. So that sigma F is equal to question mark newtons, and we also want to know direction. Hurry up, computer. So I've written the word direction. I'm waiting for my computer. All right, we'll go with it. It looks awful. Hard to write when you can't see what's being written. So let's get going with this. So the first part, what would be the gravitational attraction between the Earth and Mercury? Okay, so to do that, we would need to know the distance. I'll change colors here. The distance between the Earth and Mercury. So if I look at my handy little table up here, do I have that distance? No, I don't. I don't actually have that distance. I do have some other distances, though. I do have, for example, the radius of orbit of Mercury. So that number right there. So that is from the center of the sun to the center of Mercury. So radius of orbit of Mercury. And I also have the radius of orbit of the Earth. So let me draw it like this, from here to here. And I'll call this radius of orbit of the Earth. So what number, I'm sorry, I should have circled it too. So in my formula for gravitational attraction, what number is going to be the distance? Is it going to be the first one or is it going to be the second one? Well, it's not going to be either of them. It's going to be the difference between those numbers. So this distance here, distance from Mercury to Earth, well, what that distance is the radius of the orbit of the Earth minus the radius of the orbit of Mercury. So what numbers are those going to be? That's going to be radius of the orbit of the Earth is 1.50 times 10 to the 11th meters minus the radius of the orbit of Mercury is 5.79 times 10 to the 10th meters. And if you do that in the calculator, what number do you get? You get 9.21 times 10 to the 10th meters. So I'll circle this. This isn't our answer for part A, but this is a piece of information we're going to need. So yeah, to figure out the gravitational attraction, what do we do? So F sub big G between Mercury and the Earth is going to be big G times the mass of Mercury times the mass of the Earth divided by the distance from Mercury to the Earth squared. So now we go to the numbers. So 6.67 times 10 to the minus 11th, and I'm leaving off the unit so I have enough space. And then we need the mass of Mercury. So go to the table. The mass of Mercury is this number right here. And we'll also need the mass of the Earth. That's that number right here. So let me go down here. The mass of Mercury is 3.29 times 10 to the 23rd. Kilograms times the mass of the Earth, 5.97 times 10 to the 24th. So yeah, the Earth is much more massive than Mercury. And I've written it, and I'm just waiting for the computer to catch up. Not kilometers. Kilograms. And all of this, whoop, all right, that'll do. All of this divided by this distance that we just figured out. 9.21 times 10 to the 10th meters, and this quantity gets squared. All right, so a couple tips when you're doing this. If you get good at doing the calculator and knowing the order of operations that your calculator wants, you can do all of this in one big shot. If you're struggling to get the calculator to give you the right answers, another way you could do this is figure out the whole top part, get a number for that, write that number down. So blah, 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 blah. And then do the bottom part, 9.21 times 10 to the 10th squared, write that number down, blah, 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 blah. And then ask the calculator, what's the top thing divided by the bottom thing? And you get a number. So you can do it that way, or if you get good with the calculator, eventually you'll do it all in one fell swoop. So yeah, if you plug in those numbers and you do it all correctly, you're going to get 1.54 times 10 to the 16th newtons. So put a box around it. We solved for the right thing. We gave it the right units. So it's that. Well, on to the next part. What would the net gravitational force of this alignment be? Is it towards or away from the sun? So in parts B through D, you would just keep doing this same trick and keep figuring out all the different distances from, Venus to Earth, from Mars to Earth, from Jupiter to Earth. Plug in their masses into this formula. Yep. Into this formula. And then keep getting all those numbers. So eventually you would have all those numbers. And now you get to part E. So we've got to figure out, hopefully I can squeeze all of this in. We've got to figure out what would be the net gravitational force of this alignment. So, all right, notice which way the planets are all arranged relative to Earth. So Mercury is to the left of Earth. So is that going to be a force to the left or the right? Well, it's gravity. So Mercury is going to pull. Let me change colors, actually. Go to a purple. Earth is going to feel F sub G, Mercury and the Earth. That's going to be to the left. How about Venus? I'm going to write it down here so there's enough room. That's also going to be to the left. So this would have been our answer for part B. Force of gravitational attraction between Venus and the Earth. And then what about Mars? So that would have been going this way. I'm just going to call it F sub G M E. Just know that this M is for Mars. And then what about Jupiter? Well, that's also to the right. So the force of gravitational attraction between Jupiter and the Earth. All right, so how are we going to add these vectors? Well, you've got two of them going to the left and two of them going to the right. So the ones going to the left would be negative, and the ones going to the right would be positive. Oh, didn't mean to do that. Let me come back. So how could we write this? So here we are doing part E. There's a very hat way to do this. You could say sigma F, so all of the gravitational forces that we're dealing with on the Earth, is equal to F Mercury on the Earth with a hat plus F Venus on the Earth, also plus with a hat, plus F Mars on the Earth with a hat, plus F Jupiter in the Earth, also with a hat. And then we've got to deal with the hats. So we have to guess which way this force is going. I'm going to guess that the force is going to the right, so sigma F would get a plus. And then when we actually go to the numbers, this one, let's go back and look at the sketch. So that first one is going left, so that one would be negative. The force from Venus is also going left, so that one would be negative. Force of Venus and the Earth. Force of Mars, again, different M. That's going to the right, so that would be positive. And then the force of Jupiter on the Earth, also going to the right, that one would be positive. So then you would add up all these numbers that you got for your answers for part A through D. And when you do so, eventually you will end up with a number that is 8.47 times 10 to the 17th newtons. And it is a positive number, which means the force is going to the right. So in the sketch I made, going to the right means away from the sun. So it would be this, away from sun. So put a box around it. We solved for the right thing. We gave it the right units. We figured out the direction too, which we were supposed to do. So we're happy. So we give it a check. So kind of the moral of the story with this, and throughout this whole chapter, is make the little sketches, because the little sketches are really key to figuring out what all your numbers represent. Because people in the past have gotten in trouble, especially when they're doing a problem like this for part A. So maybe they even figure out, what formula they want. They know that they want this formula. F sub G is equal to big G M1 M2 over D squared. And maybe they can figure out M1 and M2, but they're going to struggle with D. And they're going to assume that D has to be one of the numbers in this table, when in fact, the D in this problem was not any of the numbers in this table. It was the difference between two numbers in this table. So if you have your sketch, let me circle my sketch right here. Whee! So if you have your sketch right here, it should be not too difficult to see that, for example, this first distance we needed, from here to here, was the difference between the radius of Earth's orbit and the radius of Mercury's orbit. So make the sketches. Hopefully you found this helpful.